Hello, my name is Dylan, and I provide additional support in physics and math at the Broward College Academic Success Center. I'm also a teacher at St. Thomas Aquinas High School in the Department of Mathematics and Statistics. I have a BS in physics and an MS in math with an emphasis in post-secondary math education, and I have 3 publications. And this is my second example in applying Newton's second law for inclined planes. So a 5.90 kilogram block is being pushed up an inclined plane with a force with magnitude 14 newtons. If the ramp is inclined at 25 degrees and the kinetic coefficient of friction is 0.146, what is the acceleration of the block? So I started by identifying my variables. I know mass has units of kilograms, so I labeled my kilograms M, and so on. Just keep in mind, mu, this Greek letter mu, is the symbol for the kinetic coefficient of friction. So let's identify those forces. So we have the applied force, just someone pushing the block up the ramp. This is F. We have the normal force, N, which is the force of the ramp itself pressing up against the block. There's friction. Acting to the left. That's because the force in red pushes the block up the ramp. If that's the case, that red force causes this motion acting up the ramp. That's our acceleration. So if motion occurs to the right, then friction opposes that motion and occurs to the left. Finally, in purple, we have our weight or force due to gravity. I'll call it W. But now that's going to be broken down into a vertical component. I'll call that WY, and a horizontal component, WX. Now, again, according to Newton's third law, forces can balance each other out. So if the ramp itself is pressing against the block, that causes the normal force N. But to counteract that, the converse holds true. The block presses against the ramp, and that's what WY is. WX is the gravity pulling the block down the ramp. So anyways, let's get started. Oh, and also remember this angle here at the top will always equal the angle of the ramp. So what you're going to do is find the sum of all forces acting in the horizontal direction equals mass, horizontal acceleration. What are the horizontal forces? Well, the friction, the applied force, and WX. Okay. So we have the friction, the applied force, the friction, the WX equals MA. So F. Now we have a number to plug in for capital F. There's just a numerical value we can substitute in place of that. So we leave it alone. Plus, it's just some generic force. There's no set in stone equation for that. The friction, on the other hand, what color did I use for that? Orange. Friction always has a set in stone equation. Well, somewhat. It's always mu times n, but n itself has no formula. So it's kind of weird. Because yeah, normal force, it has no set in stone equation. Its expression varies from problem to problem, which actually means in turn, the equation for friction would vary. But anyways, you'll see in a moment. So this is going to be mu times n minus wx. I'm going to replace wx with mg sine theta, because again, w always equals mg. On an inclined plane, wx is always mg sine theta. wy is always mg cosine theta. So those are like your formulas for an inclined plane. Now this expression would equal to ma, but I'm going to divide both sides by m, because our goal is to find acceleration. So we basically did. Okay, so, but as I said, normal force has no set in stone equation. So although our ultimate goal is to find acceleration, we hit a roadblock and we have to go off on a tangent to find normal force. Now, normal force is a vertical force. So we apply Newton's second law in the y direction to build an equation that contains all vertical forces, including n, and then we isolate n using algebra. Ay is always 0, 99% of the time. Because no motion occurs in the y direction unless the block is vertically lifted off the ramp. But it's not. It's in contact with the ramp the entire time. So the left side, all vertical forces, would be normal force and wy. That's it. So we have the positive normal force and the wy. This equals m times 0, which is 0. So normal force equals, it is wy. They're equal in magnitude. But then I could replace wy with mg cosine theta. So this is equation 2. So finally, again, we have to solve for n to solve for a. We've completed our roadblock. We found the expression for n. So we go back to equation 1 and replace n with its expression. So again, equation 1 said, I'm just going to rewrite it so it's clear. It was F minus mu times normal force, but normal force has no set in stone equation, so we had to find it, minus mg sine theta, all divided by m. So now when you replace n, we said n was mg cosine theta. And then we still have the second term, mg sine theta. And the entire denominator is the mass. We could simplify this one more time. I mean, you don't have to. At this point, you can plug in all the numbers. You don't have to do any algebra. But if you want to reduce it a little bit, notice that both terms contain mg, and both terms contain the negative. So you could factor out a negative mg. I'm going to actually do that because then it's easier to plug into the calculator. So f minus mg. So if I factor out mg, all that remains is mu cosine theta minus, no, plus sine theta. Yeah, maybe we should be a little careful doing that algebra. Again, notice how we factored out a negative, so this becomes a plus here. Because if I were to redistribute this back in, we'd get our previous line. And our previous line was negative mu mg cosine theta minus mg sine theta. So finally, A would be the force minus m g is 9.81, acceleration due to gravity. Mu was 0.146 cosine of 25 plus sine of 25, all divided by m, which was 5.90. And you could have even simplified, you could have done another like algebra step, and you could have divided each term by m individually, and that would allow the masses to cancel. But anyways, this is more than fine. So again, that's going to be 14 minus, what's that product? 5.90 times 9.81. Good, so we get about 57.9 times everything in these brackets here. When I type everything in the brackets in parentheses, it becomes about 0.555. Again, this is all divided by the mass, which is 5.90. So when I type this into the calculator, we get about negative 3.07. Now this is an acceleration, so it's units of meters per second squared. Oh, okay. Wonderful. Now, let's provide a physical interpretation for this. Is there a contradiction? Our calculation unfolded numerically as a negative acceleration, and that seems to contradict our diagram. In the diagram, we specified that acceleration points right. Now, acceleration is ambiguous. So although the vector points to the right, and it seems to contradict this negative number here, that's actually allowed. Now, only the velocity vector truly indicates the direction of motion. But yes, in this case, motion still occurs right. You may be thinking, wait, I have a negative acceleration. Does that mean the block is moving down? No, it's still the case that the block is moving up the ramp. But again, this is ambiguous. If you truly wanted to know the direction of motion of the block, you'd have to rely on the velocity vector. If your velocity is negative, that means the block has to be moving down or left. And in this case, again, the negative acceleration could indicate that the block is moving up, but it's simply the case that it's slowing down. Oops, that looks like, yeah, it's one word. So the velocity or the acceleration is pointing in the right direction. It's okay that it's pointing up. The block is moving up. But then what's the meaning of the negative acceleration? It just indicates that it's slowing down. So that's how you would calculate it and reference your diagram to interpret your motion and see if it's correct.